announce the first speaker, Marjeta Kramar Fijavž from University of Ljubljana. The title of the talk is Flows on Metric Graphs in General Boundary Conditions. So please.
Thank you. So sorry again for this delay. So I will try to be shorter. So as you see, I have some, this is the plan of the talk, and I have this example section at the end, so I can be shorter here, so I can skip some examples if needed. Okay, so the main topic is flows on metric graphs. So let us start explaining what I mean by it. So we will consider a graph as it is depicted here. So we have some vertices, we have some edges, and this graph is finite, which means that we have finitely many vertices and finitely many edges. It is connected. This is clear what it means. And it is non-compact. What does it non-compact means? That actually we have some edges that are that have both ends, and then we also have some edges that go to infinity. Okay, and then what we do, we parameterize these edges. So we have this this part, for example, these compact edges. We parameterize them as intervals. And to keep everything simple, we will have just 0, 1 intervals. And this non-compact part, which is here, these are the parameterized as semi-axis, like this. So we have a bunch of intervals. We will have, I think we will always use M compact intervals and L semi-axis. And then on each of the edges, we take a transport equation. So this J actually represents each of these index for each of these edges. We have a function U, which represents, I don't know, some density or distribution or something of the material in time t at position S. And then the time derivative equals some space-dependent coefficients times the space derivative. So this is the simple transport equation. Okay, it is not the simplest because we have these coefficients here, but still we don't have anything else here. And then, so we put this equation on each edge, and then we need to say what happens here when the edges come together. And sorry, is it okay? Everything?
Yes, agree.
Oh, okay. It was a phone and then disrupted my, sorry. Okay, so. So we have boundary conditions in the vertices, which are could be, for example, typical boundary conditions are the Kirchhoff conditions that you say everything that comes in also flows out, for example. So let's say like this is called the standard conditions would be the sum of the inflow equals the sum of the outflow. This is like Kirchhoff. This is an example of conditions, and usually one needs to add something else. One needs to add some distribution rules. For example, if we say something is flowing here, then and we have to say 1/3 goes here, 1/3 here, 1/3 here, for example. So these are the so-called standard rules, but one can also take something else. And we also need some initial conditions to have the whole problem. And of course, our main question is, when is such a problem well posed? And we start, before continuing, let me just mention some authors that already investigated similar problems. To my knowledge, the first paper that dealt with flow or transport equation on a network was in 1996. Barletti, with only 2 T, sorry. He was considering linear Boltzmann equation on a network in an L2 settings. Then the next time that somebody considered this was in 2005, when I considered this together with Esther Shikolia. And then there are a bunch of names here. They all come from Tübingen School, where we started to work on this problem using the operator semigroup tools. We were studying transport in L1, usually, or also we went also to LP. The question, we were not just the usual transport expression, but we can also equip it with, I don't know, delay or some other things, or we study control, or we study infinite graph, etc., etc. So I'm sure I forgot many names here. Then let me mention 2 other schools or approaches. One goes to the next speaker after me, Jacek Banasiak, and his PhD students who are continuing in this line where we started, actually, I would say. Also have several results and also maybe some relation to biology, some applications. And then independently, there is also another group of authors who study this problem with another tools using the system theory, Port Hamiltonian approach on L2 or even LP spaces. And they also have similar and also different results. And of course, there might be many more people, which I cannot mention here. What I want to stress is that actually all this work, usually they all consider compact graph. The only non-compact are the last part here, the last names here, where they considered star graphs. So graph which some semi-axis attached to a vertex. So this last authors, I think it was, I don't know, maybe 2019 or 2020, where the first papers appear. Okay, so what we want to study today, we will consider non-compact graphs and also not necessarily just stars, but something like it is written here. So we can have some compact part and then we have these rays going out. Our coefficients will be general. So in starting works, usually the coefficients are either constant or they are, I don't know, they're rationally dependent or not dependent, stuff like that. In our case, they are even space dependent. Okay, so they're not constant along an edge. We will start directly in LP spaces for any p greater than 1. And what we will treat are quite general boundary conditions, not just the standard one. Most of the works that were cited in the previous page considered standard conditions, but we will just try to be as general as possible today. And our aim is to obtain necessary and sufficient conditions for the well-posedness of such a problem. Okay, our main tool are the C0 semigroups. And so what do? We first formulate this problem on a graph as an abstract Cauchy problem of this familiar form. So we have to choose the appropriate space and the appropriate operator. So the space will be the LP function. So these are, again, these two parts that I was having before. So this is this with the infinite, so non-compact part, and this is the compact part. So you see we have M edges that are compact and L edges that are actually semi-axis. And I don't know if I will use it later on, but let me denote it anyway. So this is so-called external part, and this is the internal part. So this is compact, and this is the non-compact. And we will be studying functions living on these edges of this graph. And the operator is this guy. So these coefficients depend on space and the space derivative. Let me stress here that you see that this is not a diagonal. So this could be non-diagonal matrix, this coefficient matrix, okay? And then we need to couple all these things together. So what is the domain of this operator? Okay, these are the functions living in the first derivative should be in LP on these spaces, but then here we have the boundary conditions. So here are our boundary conditions. Are hidden in this so-called boundary operator. And boundary operator is mapping from this space to our boundary space, which I still did not specify. So this is our boundary space. And what is boundary space in our case? So when we started to work on this problem, I always imagined boundary space are actually the vertices. So this is where, in this graph, where all these edges come together. So this is where we need to pose the boundary conditions, right? Okay. Actually, in this transport case, it is, in non-compact case, it is not necessarily the case that all the vertices are in the boundary. I will explain this, I think, in the next page. So maybe I'll just, before I go to the next page, so this is our abstract Cauchy problem, okay, with this generator. And of course, our goal is to prove that this operator A generates a C0 semigroup. Then our problem will be well posed. Okay, now let us go. I still owe you an explanation. What is this boundary space? First, let me tell you what are our assumptions. So these coefficients that are there in the transport equations, you can say they are sort of velocities. They should be all bounded, of course. And these conditions is quite important. I said that this does not need to be diagonal matrix, but it should be diagonalizable. So one can diagonalize this matrix in such a way that these matrices here are bounded Lipschitz continuous with bounded inverse. And then here these lambdas are diagonal entries, and this E means external, I means internal. So these are to the non-compact edges, these are inside to the compact edges. And now that I have this diagonalization, I can see, I need to explain something else. What is this strictly constant sign? This means that this along an edge, this lambda does not change a sign. Either is it positive or it is negative. So these are functions, of course. So if you have an edge here, and this is an kth edge, then lambda k of s, along this interval, it will be either always positive or always negative. It will not change the sign within this interval. So this means that we have some of these lambdas are positive and some of these lambdas are negative. And then we can denote the spectral projections corresponding to these negative positive values. And then we count. And now our boundary space is actually given here. So it is, our boundary space is like this. Now let me explain why it is like this. So we have M are the compact edges and L are the semi-axis. How many boundary conditions do we need? If we have a flow on an interval, so we only need it depends to which direction this flow goes, right? So we need to have a condition on the beginning of the flow, right? And if you have an edge, we know that actually the sign of this lambda gives you the direction of the flow. And then once you have the direction, you need to have in one vertex, in starting vertex, a boundary condition. So for all the compact edges, exactly for each of them, exactly one boundary condition is needed. So altogether we have m boundary conditions for the compact part. So this is actually this. While for the non-compact part, you would need a condition if you would have a flow going like this. But if you have a flow incoming here, then you must not prescribe any condition here. Okay? So actually, you only need that many boundary conditions as many outgoing flow you have. And this coincides with the number of negative values of lambda. So this is this. So altogether, the number of boundary conditions you need is exactly m plus the range of this matrix, so of this external, those negative values of lambda. So this is now our boundary space. It is a subspace of this guy. If we treat compact graphs, then it is easy, then we take this. But now we just need to because we don't have two ends here, we just have one end. Okay, I hope I explained this sufficiently. And the main idea we use is to consider our graph as a boundary interpretation of a set of intervals. What I mean by this, so let's say we have, I said we have like m intervals that are compact, and then I have, I don't know, L intervals that are not compact. And then actually, what do I have on each of these edges? So here I have, I don't know, here is always 0 and here is 0 to 1. The main operator here is actually the first derivative. And we know that the first derivative, we know that it is a generator of a translation semigroup. If we have these boundary conditions, for example, if it goes like this, then we have to set a boundary condition here. If it goes like this, we have to set a boundary condition here. But it is a generator. Okay, and we have these shift semigroups. Now, what do I need? Now I need to glue this. So I know I have, if I consider each of these intervals, I have a simple translation semigroup. Okay, it is a little bit, I need to
excuse me, could you mute your computer, Madhu, for example, Kadio Madhu?
Yeah. Okay, let me continue. So we need to glue the edges via the boundary conditions.
Organizer from the room A. Выключите, пожалуйста, звук вот у человека, который...
Окей.
Каджо Рафаэл, Маду. Выключите ему звук, пожалуйста. Или сделайте меня организатором, и я сам выключу.
Okay, yeah.
Рума, выключите, пожалуйста, звук у Каджо Рафаэл Маду. Или сделайте меня организатором, и я сам выключу.
Okay, please continue.
Please continue.
Okay, yes.
We will try to solve the problem.
Yes, I think it's solved now. Okay, so what do we do? As I said, we have, first we consider separate intervals, and we put 0 conditions on the appropriate boundaries when needed. Okay, and then we glue this so that we perturb the boundary. So we perturb the boundary so that it will not be 0 anymore, but the appropriate edges will be connected through the boundary conditions. And we will use the abstract boundary perturbation from the semigroup theory. So here we go again a little bit to the abstract semigroup theory, boundary perturbation of the domain of generators. Actually, today we heard some talks, maybe not all of us, but they were in room, I think B or C, I don't know. There were some talks about the result, using the result of more than one talk using the result of Greiner, who first used the semigroup theory to study the perturbation of the domain of generator. His results were for bounded perturbations. And then let me mention two other important names in this subject. So Weiss and Staffans, where actually the same was studied more in the system theory language. And then there are two other papers that appear almost simultaneously in 2014 and 2015, who somehow translated this to the language of abstract semigroup theory. And this is in the case for unbounded perturbation in the domain of a generator. So what is done there is shortly described here. So we have two Banach spaces. So this is the X, and this is the so-called boundary space. So this is the system space and the boundary space. And then we have an operator, which is called the maximal operator, though this is the operator without boundary condition. You just have the operator with its action, but you do not have any boundary condition. So this is, of course, not a generator. So you need to restrict the domain to get the generator. And how you do this? You have this boundary operator, which you would like to have at the end, but then you can write it as a sum or as a so minus L minus C of two boundary operators, such that if you take our maximal operator restricted to the domain, whose domain is the kernel of this L, then this is a generator. Okay, and our main operator, which we would like to tackle, has the full boundary in its domain. So in our case, you can imagine that this A0 would be that we take 0 boundary conditions. Everywhere we take 0. And then we know that because these are the translation semigroups, that then these are generators. And this L, of course, I forgot some assumption here. This L should be surjective. Okay, and then all these boundary abstract results here actually tell you under which condition of this boundary operator phi, A would really be a generator of the semigroup. So you know that this part is a generator, and then you know what do you need to assume for this phi in order that the whole operator would be a generator with this domain. And we use this result, how it is this, what do we obtain in our setting? Here I have written the main theorem of a paper, I think I've forgotten in the beginning when I was so stressed with the tablet. Everything I'm telling you today is joint work with Klaus Johann Engel. And we have submitted our paper actually, so it is not yet published, but it is an archive. So what is our main theorem? This is that actually one can describe the generation in terms of the invertibility of certain matrix. What is this matrix? So this phi bar here is actually our boundary operator that we had before, but we change variables different coefficients on the edges. So we do something like this. I will not go into details because it is quite complicated, but it is something we use something like this on each interval, etc. And we also diagonalize according to this diagonalization of this matrix C. Then we get this phi bar. And what are these guys here? Okay, these projections, you know, these are those positive or negative parts. And here, these Q, T, S, T, R, T are actually these shift operators, okay, that are generated by the first derivative. So this is a little bit vague, but if I would go into details, it would be too complicated. So in general, it is an operator that can be obtained from our boundary operator and such an operator matrix. And if this is invertible, then A is a generator. And this is our most general result, and this is a sufficient condition. Now I said that actually I want to have a necessary condition. A necessary condition is obtained via this theorem, which also maybe looks a little bit complicated, but it is not easy to explain. So I just wanted to give you an idea how it looks like. Then I will explain it better on concrete examples. So if we assume that our boundary operator can be decomposed in such a way that here we have a bounded operator, which is actually in our case, this guy here, this is a bounded operator of the closure of the domain of this maximal operator, okay? Then B is some bounded perturbation, which can be added with or not. And then this is important. This L is the same operator I had before. And this V is non-invertible. So maybe non-invertible V, which is here. So L is as before, and in our case, this L, so this is this operator that gives the values, the zero boundary condition. So this is these deltas are evaluation in zero, right? So delta zero, I mean this is applied to a function is f is zero, point evaluation. And of course, whenever it matters whether I have negative or positive speed, whether I need to evaluate at 0 or at 1. This is for the compact part. And for the non-compact part, I only evaluate in 0, of course, and only when I have the appropriate direction of the flow. Okay. And now what our result says, if A is a generator, then this limit does not exist. And in this limit, there is some L lambda. This L lambda is actually computed here explicitly for our case, but this L lambda is nothing else but the so-called Dirichlet operator from this Greiner theory. So it is like this, the inverse of L restricted to the kernel of lambda minus m. And this result maybe seems a little strange here, but actually this gives us a necessary condition. So how do we apply this? Remember here we had, if this R is invertible, then A is a generator. Then we say, okay, and what if this is not invertible? And then what we do, okay, we assume, okay, if this is not invertible, then we compute everything in our case, and then we show that if R is not invertible, then this limit is actually 0, meaning that A cannot be a generator, because for any generator, this limit should be infinity. This is how we apply this theorem. So to sum up, we are able to abstractly obtain necessary and sufficient conditions for totally abstract boundary conditions. You see, this phi was anything here. And now to get some more idea how it looks like, let me go to the special case. And this is the case when this abstract boundary operator is given in terms of some matrices. some boundary matrices. So this will be maybe more clear. So what we have here, this assume that our operator, boundary operator is given like this again. So what does this mean? This means, so let me say we have some function in X which consists of external and internal parts. So on non-compact and compact edges. And then if I write this is our boundary conditions. Now, if phi is the matrix given below, then we can write it like this. F in 0 plus V0I F in 0 minus V1 I F in Y equals some BF for some bounded operator B. You see, these are matrices. So these are now boundary conditions for some matrices V0, V1, E or I. And what is our result? If we have this transport process with such boundary condition, then A generates a C0 semigroup. If and only if, you see, we have a characterization, this guy is invertible. So we have, this is this R in our case, can be computed. And what does this mean? If you take a look in here, actually you see these matrices appear here, those matrices from the boundary condition. Then we have, it is important whether we have positive or negative signs. We just project to those parts. Also, these Qs appear. These Qs were those matrices in the diagonalization of the speeds. But this B, this bounded operator, does not appear here. So we can add here anything we want, and it will work. To be even more simple, we can also go to compact graphs, and we can assume that our velocities are diagonal. So what does this mean? Compact graph means that actually this L is 0. We don't have any semi-axis, we just have compact intervals. And diagonal means that these Qs are identities. So this our C is diagonal, so Q is identity. And then the same result as before, but now it is a little bit easier because we only have the internal part. So I don't even write this I anymore. So I only have this. And it is also easier because now I have square matrices. And if I have square matrices, I can talk about the determinant. So the same condition as before, this operator that should be invertible is this one now, because we don't have any, recall, we don't have this part and these Qs are gone. So only these V's and projections remain. And so we just compute, so given the boundary matrices, we just compute this determinant and we know whether the A is a generator or not. And this is even more simple. So for example, usually in all the problems studied previously, usually one would assume from beginning on, one would take a preferred direction. So one would know a priori all orient the edges and you know which direction is the flow. So for example, if all, this means if all lambdas are of the same side, this means they are either all positive or all negative, which means that one of these is projection matrices is 0 and one is 1. So we only need to compute determinant of V1 or determinant of V0. And this, one of these should be non-zero. So this is really simple condition. And of course, we know we can also have a group generator if also minus A is a generator, which means we just reverse this, you see, reverse this set. So if, for example, if we have all lambdas of the same side and we have both determinants non-zero, then we have the generation of a group. Okay, now let me go even more back directly to the graph to connect it to the network. So in the compact, let's take just the compact graph so that all velocities are, for example, negative. This means that if we have an 0, 1, then we have the flow goes from 0 to 1. And the standard Kirchhoff conditions are written like this, right? We assume something in if I have, so if I have here some flow going in, some go out, I say whatever comes in with some coefficients should go out with some coefficients. So this equals this. These are these matrices with coefficients. And by our result, A is a generator if and only if this guy is invertible, because we only have negative part. And in this case, when this one is invertible, one can write this condition in such a way that we put this invertible matrix here. This is what we have here. And this is the usual, another standard way to put some, usually maybe it's even some other letter here, maybe B, which incorporates the structure of the graph. So the values of our function is 0, is given by some matrix applied to the values in 1, and this matrix incorporates the structure of the graph. Usually this is the weighted adjacent matrix of the line graph. So we get this. Now, if we want to proceed similarly in the non-compact case, if we again assume that we have velocities which are diagonal, and again assume that this is non-negative, all velocities are negative, then we just do as here, but instead now we also have this external part, right? So the external, in 0 we have the external and the internal, in 1 we only have the internal. And our results tell us that actually A is a generator if and only if this matrix is invertible, which means it has full rank. This is this Q that I had before, which is Q denoted. So the number of negative external eigenvalues plus M. And of course, in this case, when this rectangular matrix has full rank, it is more Penrose invertible. And if you write this inverse, we can write the boundary conditions like this. So this would be the new B in this case. So that we have, and I have, yeah, it is okay. So the functions in 0 are obtained via some matrix to the values in 1. Okay, now let me see. I have a couple of minutes, I think, to go to the even more complete examples. Here I have an example of so-called pumpkin graph. So we have 2 vertices and 3 edges connected, and this arrows means arrow is always means, so the lambdas are negative, so the arrow tells you that here is for the E1, here is 0. So here is 0 and here is 1, but for E3, it is parameterized here 0, here 1. Okay, and if I write here, what would be the possible boundary conditions? For example, let's say, okay, here I see what goes in. Let's say boundary condition 1.
Okay, I found this on the web for what goes in. Check it out.
Sorry, I don't know, what was this? So boundary conditions 1, I would say U1 in 0 plus U2 in 0. So both functions in here should be the same as this one, right? U3 in 1. And then in the other vertex, U3 in 0 should be the same as U1 in 1 plus U2 in 1. This is like conservation, right? And now if I write the appropriate matrices, what would be here now the appropriate matrices? So V0, this would be a matrix that I need to collect the coefficients here, right, with 0. So I have 1, 1, 0, 0, 0, 1, and it should be 3 times 3. So, but I have just 2 equations. And then what is V1? On the other hand, we have, so if I want to get this equation, if I evaluate this in 0, I should get here U3 in 1. So it would be 0, 0, 1. Here I would have 1, 1, 0, and here again 0. And if you see, this is of course not invertible, which means that our problem with these boundary conditions is not well posed. Why? Because we have just two conditions. You see, this is this. We do not have enough boundary conditions. So we need to change this. So this is the classical mistake that at the beginning everybody makes. We think we have two vertices, so we need two conditions, but it is not the case. We need three conditions because we have three edges. And the conditions would be, I don't know, we have to say, for example, U1 in 0 is, I don't know, one part of U3 in 1. And U2 in 0 is 1 minus alpha, for example, if you want conservation, U3, 1. So everything that flows in here divides alpha, goes here, and 1 minus alpha here. And then the third equation could be as before. And now we have this matrix is just identity, and the other one is, what is this? 0, 0 alpha, 0, 0, 1 minus alpha, 1, 1, 0. And you see that this guy is invertible, so we have C0 semigroup generation. So this is a very simple example. I have a few examples, but maybe I will skip. Maybe this one I will just mention it. So this is a similar situation, but with non-compact graph. And we can, and I have put some say coefficients here, and I can see that A is a generator if and only if, for example, these conditions are non-zero. One can characterize. But let me go to more interesting example. Here I want to go to stress that why did I consider non-diagonal velocities? Because it does matter. So if I change these coefficients here, I was always saying I didn't have any Qs, and it was simple. But if I also have these Qs, for example, if we take this matrix, this satisfies all the conditions that are needed. And we had before, if our boundary condition is the simplest, so evaluation in 0 equals the evaluation in 1, our condition, this is very simple, just two intervals, right? We know that A is a generator if and only if this guy is invertible. And now assume if, first of all, if both lambdas are of the same size, then either this is 0 or this is 0, and then we get invertibility because this is also invertible and this will be okay. But if they are of difference of the opposite sign, and even if we take the identity matrix here, then when you compute this matrix, I don't have now time to compute it, but if you compute it, you will get a singular matrix. So you see that these are important, this coefficient. But if you take like identity, then we obtain the generation of the C0 semigroup. Okay, so I don't know, do I have time to explain this small example? Or?
Yes, I think that you have.
Okay, then let me end with this. Let me end with this very last example, because I wanted to show you also that non-local boundary conditions are possible here, which maybe make not so much sense because you have graph and you say, I'm always saying all the time that the boundary conditions should somehow reflect the structure. But anyway, it can happen that in boundary condition, you have the structure of the graph, but also some information from some other parts come into place. right? And this, and to illustrate this, I will just use a simple one interval. So one dimensional, even no network, and the simple first derivative. And the boundary condition is like this. So evaluation in one is some operator B, which is given here. Actually, this comes from biology, and I think it was already present in one of the talks today regarding some cell maturation, McKendrick's condition, right? So this says that actually the value at one depends on the value of this function on the whole interval. And so we can treat it with our setting. So what we have compact case, so M equals R, L equals 0. Then, okay, we don't have matrices, but we have actually numbers. Evaluation in one we do not have, but we have one evaluation in one, or we can also, if you put it on the other side, we can have it -1. Then we do not have this, but because this one is a positive sign, you see, so we have this. And then you compute, and all these together, you see it is -1, right? So it is invertible, it is not 0. So we have a C0 semigroup, but this guy is 0, so it is not a group. Very easy consequence of our result, but I just wanted to mention because it was even present today at the conference. Okay, now I'm done. Here are the references. So this is the paper where all these results are inside, which is published on the archive. Here is a predecessor of this paper where everything with this almost the same technology is done for the diffusion and wave equation. Then I also applied, together with Alexandra Puchalska, all these results to a survey paper on semigroups for dynamical processes on metric graphs, where we also can find more references on the subject. And at the end, I invite you all, to those who are interested in the contents of this talk, to join us in our cost action project. All information are found in this website. Okay, thank you.
Thank you for a very interesting lecture. And questions, comments, please.